Hey everybody. So here we are with another circuits problem. Um, a lot of students are probably looking at this and going, what is that? This doesn't really look like what I'm used to. Why are these R's in my circuit? All right. Here we go. We have a current source given as IS, it's unknown. All right, and I have 1, 2, 3, 4, 5, an array of resistors connected to my current source. 5 resistors, all value R, where R is unknown. All right. Then they go on to tell you that there's a voltage on this first resistor called the output voltage, V out or VL. All right, V naught, whatever. Now, all they tell you is based on this configuration, the V out is equal to 50 times IS. They say just with this information, what is R equal to? All right. When I say R, if all of these are R, they're all the same value. So when I find R, I'm going to be finding what every one of these resistors is. Each of these resistors is the exact same value. That's all that they're saying. All right. And I got to find out what that value is. So a lot of students who are used to having numbers are saying, well, what can I do with this? I don't have any numbers but the 50. You don't need numbers. The 50 IS was literally all that you needed. All right. You want to get used to seeing circuits like this because this actually goes into design. All right. If I wanted to design a circuit and I only had maybe one type of resistor, I wanted to design a circuit. Maybe someone gave me a constraint that said we only have this type of resistor and we want to produce this type of circuit, whatever this circuit represents in real life. Then how would you design it? This is how you would design it. All right, you'd have to start kind of throwing together what you know. Say, well, if these are all R, then once you solve it, you can get a sense and say, okay, this is the type of resistor that I need, and you can buy 5 of those, and then you'd be good to go. Instead of having to go buy maybe some variety, maybe that'd be more expensive or something like that. All right, so get used to seeing this type of stuff. So let's get to it. I want to find R, and I know the voltage is right here. Well, if the voltage is right here, I could use KVL and KCL and Ohm's law to solve my circuit. But that's what, 1 loop, 2 loop, 3 loop, 4 loop, 5 loop, 6 loops, and then 1, 2 nodes. That's 8 equations that actually would go into representing this circuit. I'm not going to do that. No, there's no way. This small circuit does not need 8 equations to classify it and to get a good sense of what's happening. I actually recommend, if you see a circuit, the KVL and KCL is most often the last thing that you want to try to do to solve it. Most often. Not always, but most often that's probably the last thing you want to try. The first thing you want to try is looking for current and voltage divider. If you can't see that, then try to reduce the circuit. All right. So I don't see any current and voltage dividers. This once it comes here, the current breaks off and then the current breaks off again. That's not a parallel anymore. It's just some sort of mess. So that doesn't work. I'm going to try to reduce this circuit. All right. So let me reduce it and see what happens. If I put these two together right here, these two are in parallel. I should have labeled my nodes. Let me put some nodes on this bad boy. I'm going to call this A. I'm going to call this B. I always put A and B around the element of interest. That means this would be C and this would be D. All right. This R is between C and D. This R is between C and D. Okay. Because these two are in C and D, these two are in parallel. All right. I know they look like they're in parallel, all right, but don't ever look at something and say, oh, they look. No, do not do that. Always do what I'm doing now. This is between this and this. This is between this and this. Therefore, they are in parallel. Okay, that is the best and only way to go. Now, here's a shortcut. Instead of me saying R times R over R plus R, I could just remember if I have 2 resistors of the same exact value, the answer is going to be the resistor divided by 2. All right. So, draw out my circuit with the shrunken piece. This is what I cared for, VL. This is R here. 1, 2, 3. And now instead of, let me clean this up a little bit. It's ugly. And now instead of having that parallel branch over here, it's just 1 resistor. So instead of this being R, this is now R over 2. All right. R cut in half. This is R and this is R. It's been shrunken, however you want to pronounce that. All right. From here, we want to see if we have any other situations. Well, this is A and this is B. Okay. Between A and B is R. Between A and B is this, and this. If I were to draw a current, spontaneous current, just passing through, it would come just like that. It would go through all of those without ever breaking off into some other path. All right, that path would never exist. So what I have is that these 3 resistors, R, and R over 2, are in series. Okay, so my equivalent is going to be R plus R over 2. That's 2 over R, 2 over R, I'm sorry, 2R over 2, 2R over 2, and R over 2. That's going to be 5R over 2. All right. So I have now 3 has become 1. And I'm going to get this current source, the resistor. This is the voltage that I cared about, R, IS. And instead of 3, I just put 1 right there. All right. That's going to be 5R over 2. Okay. And now, if this were A and this were B, then these two together are both between A and B, and I'm going to combine them. Now, the rule on combining things, these aren't parallel. Some people are looking at me saying, how can you combine them? If you combine them, you'll destroy the V out. No, you will not. All right. The rule on combining stuff is you want to combine stuff such that you do not destroy what you're looking for. I'm not looking for, okay, technically I'm looking for R. But what happens is everything has R. So even if I combine them, I'm still going to have an answer in terms of R. All right. So I can combine them on that idea. Another thing is if I combine these, I'm not going to lose my VO. Remember, what's between A and B always all have to have the same voltage. So if this is between A and B, this first R is between A and B and it has VO, this R right here also has to have VO because it's also between A and B. So remember, when you combine resistors in parallel, the voltage has not changed. So what I'm going to have is, oh man, the parallel connection is going to give me 5R over 2 times by R over 5R over 2 plus R. All right. And that's a mess, but it's okay. So what was then 2 is now 1. And that's going to be just this horrible thing. It's going to be, this looks like 5R squared over 2 divided by 5R over 2 plus R, with the voltage still existing, and then IS. And once we're here, we're almost done. Once we're here, we can go and figure out the answer. All right. Why? Because I have one current, one voltage, one resistor. Simple V equals IR. The voltage attached to this is getting that current. All right. If you look at it, the current is going to pass from the positive to the negative. So it's going to follow passive sign convention. All right. All I have to do is say V out equals I times by my R equivalent, which is that thing. V out in itself, we know, is 50 IS. Okay, this statement right here, this is IS, excuse me. This statement right here is what we need. If you pay close attention, IS on one side, IS on the other side, they cancel. REQ, which is this mess, equals 50. Okay, so from here, I just solve it. I'm going to have 5R squared over 2 over 5R over 2 plus R equals 50. I'm gonna multiply this over here. I'm gonna get 5R squared. Actually, you know what I'll do? I'll multiply the top and bottom on this side by 2 over 2. 2 over 2 is the same thing as multiplying by 1. So I don't really need to worry about doing it on the other side. So I'm going to get 5R squared divided by, and this is going to be 5R plus 2R, and that equals 50. Okay. Then I'm going to multiply this over here. I'm going to multiply it. I'm going to get 5R squared equals, I got 50 times 5, which is about 250 R. And then, oh wait, this is 7R right here. Great. That's convenient. So this right here is 7R. So instead of having to worry about the 250R, I just do 5 times 7, or 50 times 7, excuse me. 50 times 7 is 350, and that's going to be times by the R. All right, I divide by R and I divide by 5. I get R equals 350 divided by 5, that's going to be 70, and then the R cancels. R cancels on one side, 70 ohms. This is my answer. Okay, so don't freak out if you see something like this where you get a bunch of variables in your problem. It's okay. You solve it like normal. When you solve it like normal, you're going to get a formula at the end, an equation at the end, and you just solve your equation. All right. So it's almost like them saying, instead of I guess if you were to think about the directionality of solving a problem, normally you guys are used to having R and V and I be, or R and I be known, and you would solve for V. So I guess that's a forward point of view where everything is known on the circuit in the beginning and you find what's happening at the end. In this case, we're doing something like a backward point of view where they tell you the answer that you would have been looking for from the forward point of view, and you have to basically work backward, almost do some sort of reverse engineering to get to your answer. But the ideas governing the situation are exactly the same. So you treat the situation exactly the same. You just reduce it until you have one resistor, one unknown. You do V equals IR, Ohm's law, and then you solve that equation, and out pops the unknown term. Okay. So practice this. Practice makes perfect. All right. If anybody has any questions, still after this, feel free to shoot me an email or text or whatever. Okay. I hope this helped.